this paper, where it falls in kind of Marshall's rubric, is less about new geospatial data and more about developing a new way of thinking about a question that many of us have worked on, which is climate change and inequality at a global level. Okay, so we're going to use geospatial data that many of you guys might recognize, but what we're going to do is develop a new framework in which we can actually think about inequality in a way that is a little bit more sophisticated, offers a little bit more sophisticated treatment of trade, global trade around the world. Okay, so this is joint work with Solomon as well as Jonathan Dingo at Chicago Booth. So we know that climate change is a global event, and as a consequence of it, it's going to generate winners and losers around the world. Okay, so if we want to think very carefully and do like a full accounting of what climate change is going to do to inequality, there's actually two parts to this exercise. We need to understand how climate change affects productivities around the world locally, but we also need to think about how it affects the global pattern of trade, right? That is, what climate change does is that it doesn't just make Kenya hotter and Ethiopia hotter, but it makes these two locations hotter at the same time, whereas it might make Northern Europe and Canada cooler in a relative sense, right? And so that's going to change the spatial pattern of productivities around the world, okay? So what we're going to show in this paper is that global inequality is going to depend very crucially on how spatially correlated productivities are around the world. And that is going to be driven by climate change. As we're going to show you evidence that climate change is going to increase in spatial correlation around the world. And that's going to have a direct consequence on our forecast of how unequal the world is by, for example, the end of the century. Okay? And in particular, we're going to show that the standard approach that we have implemented up to this point for estimating inequality under climate change has grossly underestimated what true inequality will look like when you take into account these spatial changes. Okay, and I'll be more explicit about what that means. Paper has 3 parts. I'll walk you through each of them. The first part is just to show you some very standard trade theory that says, holding all else equal, an increase in spatial correlation of productivity increases inequality around the world. Okay? This is a prediction from a broad class of trade models. What we're going to do is we're going to try to empirically validate this, looking at global food production and trade data over the last 50 years, and we're going to use a particular source of variation in the global climate driven by the El Nino Southern Oscillation to basically drive exogenous changes in spatial correlation around the planet historically. We're going to take these estimates and we're going to apply it to what's otherwise a standard climate change projection, but adding this extra component, we're allowing the spatial effect to play in. What we're going to show is that inequality by the end of the century is 50% higher when you take into account these spatial effects. Okay, so to summarize what that means, here's a plot of forecast of variance of welfare across over the course of the 21st century. Think of it as inequality. The gray line is more or less the predictions that we've generated up until this point, looking at local to local effects. When we include climate-driven increases in spatial correlation, changes in patterns of trade, you get the red line, which if you just take the ratio of one over the other, is 50% greater by the end of the century in terms of the amount of inequality that climate change is going to generate. Okay, so very quickly, what does this mean? So the standard definition in trade is, any location's welfare is just going to be the sum of its welfare and autarky, which is just productivity, okay, and its gains from trade, okay? So across a broad class of trade models, you can actually write this more precisely, which is autarky you can think of as just, welfare when there's no trade, that's just productivity, and the second term, this gains from trade term, which is going to be captured by the domestic share of expenditure. So what is that? So what is the share of corn consumed in the US that comes from the US, okay? When that share is 1, there's no trade, okay? When it's lower, there's more trade, okay? So this is a pretty standard expression. You can write the variance version of this expression, and you can show that changes in variance is going to depend crucially on the covariance between how productive a location is, okay, and its own expenditure share, right? So what does spatial correlation do? Spatial correlation makes locations that are more similar next to each other. Okay, so in a spatially correlated world, neighbors who normally trade with each other, who are similar, end up having similar kind of draws, right? So if you do well, your neighbors do well. If you do poorly, your neighbors do poorly. Okay, and because trade costs scale with distance, when spatial correlation increases, if you're in a good part of the world, you benefit more from trade because your neighbors are doing well. Also, if you're in a negative part of the world, when spatial correlation is high, you do worse under trade. Okay, so one way to think about this is just think of the world on a line and just have a sine wave over the world. This is productivity. This is a spatially correlated world. Half of the world, which is doing poorly, is clustered in one half. Right? This is the dip in the sine wave. And the other half of the world is kind of in the hump. Okay? What happens when spatial correlation decreases? You can imagine it's like a high frequency sine wave. Okay? That is, for any given location, you don't have to go very far to find another location that has the opposite experience. Right? In the spatially correlated version of the world, if you're in the bottom right here, you basically have to traverse half the planet to find a trading partner that has an opposite draw. Okay. So spatial correlation, you can imagine, could potentially change this covariance between your own productivity and your own expenditure share. And what our theory predicts is that as you ramp up spatial correlation, so going from the blue to the green to the black to the red dots, you basically lower this relationship between your own productivity and your own gains from trade. Okay, so this is what the model predicts. We want to bring this to the data. We want to validate this in the data. What's difficult about validating this and kind of a lot of these general equilibrium predictions is that it's very hard to find exogenous variation on a global feature of the trading network. We can't experimentally vary global trade. Okay, so what we do, our kind of solution to this problem is we're going to look at a very particular climatic phenomenon known as the El Nino Southern Oscillation that on a year-to-year basis basically reshuffles productivities around the world such that the tropics, from 30 north to 30 south, experience hotter conditions in a spatially contiguous manner, whereas the rest of the world experiences relatively cooler conditions. Okay, and we're going to use that as a way to kind of test and validate our data, our prediction before thinking about climate change in the future. Here's what ENSO does. ENSO is this naturally occurring mode of climate variability. Is in fact the most important driver of year-to-year climate variability. On an annual basis, and it kind of oscillates between this cool and hot phase, El Nino and La Nina. It is captured by this time series variable, which is just sea surface temperatures over the tropical Pacific. And so this is kind of, this variable since the instrumental record in which we've had since 1860. Okay? So when I talk about the ENSO index, it's basically average sea surface temperature somewhere in the tropical Pacific. The way it affects the planet is that when ENSO and an El Nino event occurs, there's a large release of heat from the tropical Pacific that gets propagated across the planet in a fairly rapid manner. Okay? And this propagation is largely limited to the tropics. Okay? So to kind of visualize for you what this does, I'm plotting here pixel level correlations between the El Nino index and local temperatures. Okay? Pixels that are in red or orange are locations that are positively correlated with the El Nino index. When it's hot, when El Ninos are going on, this location is hot. Negatively correlated pixels are in blue. Okay, and I'm going to show you lead and lag coefficients that are going to basically provide you a sense of how heat release during an El Nino event propagates around the planet and drives the global spatial pattern of temperatures. Okay, so this is 12 months before an El Nino event. A Nino event usually occurs in the December of a given year, so I'm going to show you 12 months before and 12 months later. This is using 50 years of high-resolution temperature data. Okay, so 12 months, 11, 10, 9, 8, 7. This is usually around month May, where there's a large release of heat in the tropical Pacific. This is a characteristic warm tongue of the El Nino event. And what you're going to see in the following 12 months is that this heat is going to basically propagate going to in the eastward direction, and it's going to basically envelop the tropics. Okay? So June, July, August, September, October, November, December. This is a contemporaneous correlation. And then it intensifies. So this is now 2 months after the El Nino event. You can see that basically much of the tropics from 30 north to 30 south is hotter in a spatially contiguous block. So this is the natural experiment you can think of that's allowing us to validate this theory. We have this naturally occurring climatic phenomenon that's basically making half the planet, the tropics, hotter, and then it dissipates thereafter, 12 months later. Okay? And what we can show is that if you were to plot the El Nino index against the global Moran's eye in agricultural productivity, you see a very you see a positive relationship. That's when El Nino occurs, there's an increase in spatial correlation, it's captured by Moran's eye, of global agricultural productivity, okay? So we're gonna validate this prediction. This data is pretty standard. We're gonna use look at agricultural trade variables that allows us to construct own expenditure share as well as productivity. And our idea is basically to use El Nino to drive both local productivity and this global spatial correlation in yields. This is the main result from our empirical validation when this is for 3 different states where we're going from, in the solid line, lower spatial correlation to increasing more spatial correlation. And what you see, consistent with our theory, is that as spatial correlation increases, this relationship flattens, okay? So what can we do with this? We can think about applying this to a climate change projection. What do we normally do? Our standard method in projecting climate change is to basically relate local temperatures on some local economic outcome, implicitly assuming that kind of the allocative effects or the general equilibrium effects that we have historically estimated are held fixed going into the future. And then we say, what happens to the world in 2100? Okay, so this omits the fact that climate change can actually drive spatial correlation. So what we're going to do is we're going to take the standard approach, include our own historically estimated effects that's coming from El Nino, and show the following. We're going to show, one, that we predict an increase in global inequality under climate change. Second, that this prediction is going to be much bigger than if we were just had omitted these spatial effects. And furthermore, we can actually look at which countries are affected and also which countries have we been biased about, okay? So very quickly, this is the temperature response function that we estimate. This is a very standard kind of approach. What we see when we drive our model with their standard climate projection from CMIT5 business as usual prediction, what you see in the black line is there's going to be an increase in the variance of productivity around the world. This is what we've known for quite a while, and this is what the literature has concluded. But what you also see is an increase in the blue line, which is a measure of spatial correlation. That is, climate change is going to drive an increased spatial correlation around the planet. What does that mean? If you were to just then calculate welfare, variance of welfare around the world, the blue line, or this gray line, which I've shown you before, shows what we would predict for inequality by the end of the century if we had completely omitted these spatial effects, that climate change is going to change patterns of trade. And the red line is what you would get if we included this effect. And it's 50% higher. So this is very consequential. Who are the countries affected by this? Well, here's a map. So this is, you can think of this as the difference between this is the bias that you have from a spatially naive projection, the kind of standard that we've had up to this point about thinking of climate change impacts. Here's a map of the bias. Countries in red are places that we have up to this point understated the losses, okay? We can look at this in another way. We can look at this along the axis of, in the vertical axis, the bias, and in the horizontal axis, the change in productivity in cereal yields that we predict, okay? I want you to focus on the lower left quadrant. These are countries in which climate change is going to lower agricultural productivity, right? But furthermore, up until this point, it turns out we've actually understated these losses, okay? So what are these places? Dots in red are from Africa, dots in yellow are from Asia, and dots in green are from South America, okay? So we've known up until this point that countries in South America and Africa and parts of Asia are going to suffer from climate change. But it turns out that the reality is that they're going to suffer more than we have estimated up until this point. And this is large part because, again, think of the analogy, it's not that Kenya is getting hotter independent of Ethiopia, but Kenya is getting hotter at the very same time that Ethiopia is getting hotter, and that's going to make things worse for them. Thank you.